Okay, yeah. Can you hear me? Can you hear me is the first thing you always hear Stephen Hawking say. Can you hear me? Very important. Okay, we're running a little bit late, so I've timed this at 40 minutes, so I'm going to cut one bit at the end. I think you'll be begging for mercy by that stage anyway. What I wanted to talk about, we thought, given the year that's in it and the tragic delay during the last year, nice time to renew the ideas on what is going on in CERN, what is the famous experiment all about. You might have heard of the search for the God particle, as science journalists love to call it, and it is an extremely exciting experiment. And what I really want to show you is it's more than about a search for one particle, much, much more than that. Okay, so I have two pictures there to get started with, and the first one is of Einstein. You can't move in this area of physics without Einstein. It's often forgotten in a talk in particle physics to begin with. It all comes down to one equation. I don't have a blackboard, but you all know it. E is mc squared. In particle physics, and that reminds me, it doesn't come down to, as I've heard even a Cambridge philosopher say, it's not about dropping your watch on the floor and looking at the bits inside the watch. That is not what it's about. It's much more exciting than that. What happens is the incredible energy density of these experiments. Out of that energy density, you can create whole new particles. So whole new particles come into existence that weren't inside the thing you were looking at the time. And we look at the decay products of those, and that's how we identify what was there. So it's an extremely exciting thing. The other thing I hope to convince you is it's also not about particles anyway. What particle physics in the modern world is now about is it's about, we know there are four fundamental forces in the universe around us. The tremendously exciting discovery of the last century was that at least two of those forces are very deeply connected. In a way, they're actually the same force. They really are two faces of the same coin. And since then, the big search has been to see, can we tie in the third force, that's grand unified theory, and maybe even tie in the fourth force, and that's the famous theory of everything, that all the four forces of the universe that are known will only be one force. Now, the reason I mention Einstein there is actually Einstein was the first person to start that. And in every magazine article you see in Einstein, even nowadays, you'll see somebody saying, and then he went off on a quest for the unification of forces which was unsuccessful. And they sort of forget to mention that actually everybody else has been on that quest ever since. I mean, that started a movement that has been going ever since. And one day, I think we may be successful. So anyway, that's why Einstein is there. The other thing I want to mention is Ernest Walton. By the way, it might be hard to see here. Just pray. It works if you pray. I think Ernest Walton is very, very important because from the experimental point of view, you could argue that he's actually the grandfather of particle physics because he was involved in the setting up and use of the very first accelerator. And in fact, you know, as an Irish person, I've looked into this quite a lot, and we would argue that, of course, it's known as a Cockcroft-Walton tube, but Walton did a great deal of the work. He really did, and it's no coincidence that he was the man who actually pushed the button. Cockcroft was like the manager, and they were both running on, working under Rutherford. But Walton really was hugely involved in the construction of that voltage multiplier, etc., and all accelerators that have been used since then, including the giant one at CERN, are basically based on that idea, as we'll see. Okay, so let's move on. Quick look at what we're going to do. Okay, so 3 bits. It's a bit intimidating. First, I'm going to talk very quickly about the LHC. What is it? Why the hell would anybody want to build it? And how does it actually work? Then I'm afraid we'll have to do a little bit of work. A brief history of particles from Walton to the standard model. I promise I'll try and keep it short. And then I'll go into what we expect to see at the LHC. First of all, in terms of the Higgs boson, the famous particle you've heard about. Then, even more exciting, the stuff about what we may see, which is beyond the standard model. And of course, that's what the sort of today's generation really expect, that we know the standard model is incomplete anyway. So what we see beyond. And then something related to my own field, I can't help pointing out that, you know, there's a huge link here with cosmology as well. For all physics students, teachers, and professional researchers, what's fantastic about the era in which we're living is you get this amazing convergence between particle physics, the physics of the incredibly small, and cosmology. You didn't have that 30 years ago, whereas now they're coming very, very close together. And one reason for that is, of course, that the energy densities that they're using in accelerators are beginning to come closer and closer to, you know, the sort of energy you were talking about shortly after the Big Bang. So it's a really fantastic convergence of two different fields. Very, very exciting stuff. Okay, we'd better get on. It's pretty much all of modern physics to do before lunch. So let's look at it first. There's a famous thing, you know all about it. High energy proton beams Why protons? Because they're very easy to produce. It's just hydrogen ions. So high energy proton beams smack into each other, as every boy racer knows. Head-on collision, you definitely die because the energy is twice the energy of one particular car. So it's, you know, as opposed to banging into a wall, head-on collision is much more efficient. Huge energy density, as we'll see from the figures. I want to show you a few figures. It doesn't seem that much when you look at the energy itself. And that's that whole thing about black holes. I blame physicists like myself for saying biggest energy since this Big Bang. Of course, it's really the energy density. The actual energy itself is very small for you and me. But you and me are very large. If you're a proton and an electron, that sort of energy is absolutely enormous. It's the energy density that really counts. Anyway, like I say, what that creates, out of that energy, we can create incredibly small, short-lived particles. And that's the key, that we actually create these particles, which are not in existence before that happens. And then, of course, you're into the whole business of detection and measurement. And no, there will not be any giant black holes. There is this theoretical idea of mini black holes, which is a very different thing. But a mini black hole is really almost no relation to a black hole. And I don't want to get into that. It's one of these stories that just ran and ran. It makes no sense. We'll come back to it at the end of this time, question time. Okay, why would you want to do it? I always think this is the interesting stuff. Why would you want to do it? Well, everybody knows the first part. Explore the fundamental structure of matter, as in what's inside the nucleus. Okay, the proton, what's inside the proton. Okay, the quark, is there something inside the quark? Blah, blah, blah. What's the fundamental structure? Nowadays, that gets rephrased as investigate the interrelation of forces that hold matter together. Because the forces that hold matter together are intimately connected with matter itself, and that's really how you look at it as a whole package. The second thing, of course, like I say, is the convergence thing of we also at the same time can study conditions that really pertain to the early stages of the universe. That's exactly what you're looking at, because we haven't seen energy conditions like that since then. That means we can test cosmological theory. Now, I'm giving you some figures there. It turns out when you do the math, as actually I got 10 to the 18, but the temperatures you're talking about, when I give you the beam things, the temperatures would correspond to about 10 to the 18, 10 to the 19 Kelvin. That corresponds to the universe at 1/1000th of a second. In other words, 1/1000th of a second of the Big Bang. So that's what you're looking at. You're looking at the conditions and the sort of particles that existed 1/1000th of a second after Big Bang. The volume of the universe at that stage would have been about a football. Now, how they work that out is actually quite complicated. You have to use general relativity, so we'll just take that on board. Like I say, highest energy density since Big Bang. I can't resist throwing in two things. There are two things in particular we want to know from a cosmological point of view. The first one is this business of dark matter. You've all heard about it. Astronomers think it's hilarious that cosmologists go on and on about matter, that not only can you not see it through a telescope, you will never be able to see it through a telescope. So they keep asking, well, how do you know it's there? And cosmologists answer back and say, well, look, you know, matter to us is something that has a gravitational effect. You know, if I'm heavy, you will go around me. It's nothing to do with whether I can see you. In other words, we don't demand of matter that it should interact with the electromagnetic force. We just say it interacts with the gravitational force. And that's why, to a cosmologist, it's perfectly reasonable that, you know, it's actually almost 70% of the matter of the universe would actually be in the form of dark matter. The way I would look at it is we can't rule it out. You couldn't say it's not. It's perfectly possible the matter would be of that form. Now, what we don't know is, well, what sort of particle would that be? It's called a WIMP, a weakly interacting massive particle, a weakly interacting mass particle, thank you. You know, we've no idea what the nature of that particle is. And that's one of the things that might turn up in CERN. The other thing is the good old mystery of antimatter. What is the story with antimatter? Anyway, as you all know, I forgot to say, when you create matter, actually that's not true. You don't create it. You create matter and antimatter at the same time. You have to balance the two. And that always happens, and we've done that time and time again in experiments. But the question is, but in that case, when we look around the world around us, why is everything made of matter? The only time we see antimatter is every now and then a cosmic ray decays and we see a little antiparticle, and we get very excited about that. But the question is, where's the rest of it, you know? And in fact, you could also argue is, how did we survive at all? Why didn't, when matter and antimatter get created, why didn't it basically combine again and annihilate a couple of seconds later or a couple of microseconds later in a puff of smoke? It's not clear why the world is made of matter and not antimatter. And that's a very sort of key question in particle physics in many ways, because it's what we call a broken symmetry. Clearly isn't symmetric, because we wouldn't be here to talk about it if it was. And that's one of the things that CERN will look at. What happened antimatter? And there's actually an Irish group who have a very, very big involvement with that, and I want to talk about them at the very last slide. Okay, now I can't resist showing you this. It's not supposed to be a talk on cosmology, but I always find myself going back. This is the coolest little picture I saw somewhere. What it is in one place at the one time, if you look first at the energy, this is the energy of the universe since Big Bang. In its funny units, of course, these people love to use EVs, and 1 EV, of course, is the energy that an electron gets by accelerated through 1 volt. But basically, you can see, this is the maximum of the scale here, going down to, actually, it would be infinite in a sense, but let's start here, going down to here. There's the temperature, capital T for temperature in Kelvin, going this way, and here's time going this way. Isn't it a lovely little map? Now, of course, from what I said, we should be somewhere around here, 10 to the minus 10, maybe here, 10 to the minus 12 seconds, 10 to the 15 Kelvin in temperature, probably more like 10 to the 18 Kelvin, but around here somewhere. And then in terms of energy, 100 GeV. Now, somebody very conveniently, if you go up to the top here, they actually drew. This is what CERN will do. So CERN is about down there. As opposed to what? Well, the most recent accelerator, which is doing extremely well at the moment, which is the Tevatron, is just slightly closer to that border there. And the LEP, which is the previous accelerator CERN, was about there. And that's the answer, by the way, to the black hole question, is in a way, like all scientists, we love to dress it up and say, my God, fantastic energy never seen before. But another way of saying it is it's actually just one little step beyond the last one. I mean, the last one was here, the Tevatron's here. The next one is just one more little step in the next direction. In other words, the energy is getting slightly higher. So it's not a paradigm shift, experimentally speaking. It's just the next notch up, shall we say. OK, yeah, I think that's all I want to say on that. Fine, how are we going to do it? Just remind you of some basic stats. The famous thing you keep hearing about is 14 TeV. I don't know why people don't use SI units like you and me. It really irritates me sometimes. 14 TeV is just a fancy way of saying 14 by 10 to the 12 EV. If you convert that to joules, it's 2.2 microjoules, which you and I might say, well, that's not world-shattering, is it? But it is if you're a proton and an electron. That's a very, very, very large amount of energy if you have that center of mass collision. And that nice little bit of maths here, if you remember your basic, this is just, a sort of a back-of-the-envelope calculation. But if you were to work out, what does that correspond to? Suppose we think of this thing as a giant microscope. We're smashing things together, looking at what comes out. Suppose it's a giant microscope. What would be with the resolving power? Well, every student in the audience would say, well, E is HF. And from that, I can work out what the wavelength is. So let's try that. If I just put in the figures, just did this last night. E is HF, so rearrange that, HC over lambda. So lambda is HC over E. Put in the figures there, as in 2.2 microjoules. Multiply it by the speed of light, HC, and divide by 2.2 microjoules. And what you get is something of the order of 10 to the minus 19 meters. Now you see the point. That's why we had to build the thing. Because the proton, well, let's say the nucleus is about 10 to the minus 14. Let's say proton, the wide guess, about 10 to the minus 15. Quark would be 10 to the minus 17 in diameter. So we need to be below the diameter of the quark if we're going to see the sort of things we look at. So it needs to be, that's why we need that sort of energy, is to get down to that incredibly sort of small length. See? So that's what all the money is for. OK, so what about this? You keep reading in magazines, oh, it's an ultra-high vacuum. Why would it be an ultra-high vacuum? What's the idea behind that? Anyone? Why does it need to be at the world's, most incredible high vacuum, blah, 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 and lots of money spent? Sorry?
No stuff in the way.
Exactly. Yeah, you don't want the protons to stop off and say hello to anyone else on the way. You're spending a lot of money on these two beams to hit each other. So you don't want air molecules getting in the way. That's the only reason you pump it down, but you pump it down as much as is humanly possible to get rid of absolutely anything else that might be in the way. The same goes for the low temperature. You want to get rid of any thermal motion. But the other reason you'd have low temperature as well is that one of the sort of really innovative things about the LHC is that it uses these huge superconducting magnets. And the way that goes, I forgot to do a slide on this, but we probably won't have time anyways. The way these accelerator works is the acceleration is done from a voltage. But you can't use a magnet to accelerate something, as you know, because it's perpendicular. Remember all that stuff about, well, the three directions? Yeah. It's not going to, the right-hand thumb rule, it's not going to accelerate anything because the magnetic field is at right angles to the motion of the particle. But what it does do is it controls the direction. And you steer the beams by using incredibly strong magnetic fields. Now, if you used a normal magnet, it would cost more than it costs to run the city of Geneva. So you have to use special magnets. And the idea of a superconducting magnet is, of course, that it has pretty much zero resistance. So it doesn't consume any power. And that's what the superconducting magnets, and that's, of course, what caused the problem a year ago. Hopefully, it'll soon be fixed. But anyway, so we got this giant thing with center of mass energy is the 2.2 microjoules, these huge proton beams running around, 600 million collisions per second. When you do the math again, I had great fun frantically doing up the figures for this. It's amazing how hard it is to get your hands on simple figures. But when I worked out the power in terms of energy, power is just energy per unit time. So what power does that correspond to if you have 600 collisions per second? When you work it out, it's only about 1,000 watts. So it's not a huge amount of power in terms of, but again, it's not a huge amount of power to you and me. It's a huge amount of power if you're an electron, or a proton in this case, I should say. Okay, and then just one last thing on the sort of boring stats. There are actually 4 giant detectors. The first one is the compact muon solenoid and the Atlas. These two are both, I won't say anything about them because they're basically multi-purpose. They're put there to catch everything that comes at them. They're absolutely enormous. Each one is like the size of a cathedral. You should see them. But each one, their purpose is to catch what comes at them. Then there's a very special one called Alice. And what Alice does is it won't use protons at all. Oh yeah, by the way, if you ever wondered why don't they call it the Large Hadron Collider, if that's what it is, the answer is because they're being boring scientists. It's not always a proton collider. They have to be accurate. It's a hadron collider because sometimes they're going to use ions, lead ions in particular. And the reason for that is that's a much heavier particle. Even though it'll go a bit slower, you get a different sort of collision. And what they get from that, what they want to do is they might be able to create a quark-gluon plasma, which is what you had before quarks were formed. So that's a very, very interesting experiment in itself. And then my own personal favorite is the LHC-B. The B stands for the beauty quark, or the bottom quark if you're boring. The LHC, what this will look at is the difference between the decay of the beauty quark versus the beauty antiquark, the difference between the two. And there's a UCD group that have a very, very prominent role in that, led by Ronan McNulty. Some of you might have heard us talk last year on it. It was really, really good. I learned a lot anyway, that's for sure. Anyway, this is what these things look like. Look at the size of that. That's about, I can't say it in Waterford terms because there's no building anywhere near tall enough for that around here, except maybe the cathedral. It's a huge, huge, huge thing here. This is the Atlas one. I'll just say each one contains 3 different bits. You need to be able to measure the momentum of a charged particle. You need to be able to measure the energy independently of the momentum. And then for identification, you even need to be able to measure the velocity. So you measure all those 3 parameters independently. So you can imagine there's a fair bit of engineering in that. Okay, let's move on. Oh yeah, one last thing. This is the most wonderful recycling project in the world. Funding people are always moaning about how could you spend that much money on that, blah, blah, blah. What they don't realize is actually every single accelerator ever built at CERN is being used in this experiment. Because in accelerator physics, what you do is you always have a sequence. So this one first down here, which is actually a direct descendant of Walton's accelerator. This is the LINAC. It starts in the LINAC. Then it gets swung into this tiny little yoke here, and then it goes into the proton synchrotron, which is a type of accelerator. Then it goes into the superproton super synchrotron, and then finally it's let out into the big ring. So every single accelerator that was ever in CERN is used in this. Do you see what I mean? Which is, I think, a wonderful piece of recycling. Now, a student asked me a very good question a while ago. As you can see, if you look at this, is nicely done. You know, we're coming up to reasonable fractions of the speed of light. By the time we get to this one, oh, it doesn't say it. That's a pity. It should say it. It's about 0.99. 0.999 of the speed of light here. And then here we've got 0.999, God knows how many nines. You might ask yourself, well, I mean, if kinetic energy is half mv squared, why are they spending so much money and so much effort into getting just a few extra nines there? I mean, you're only increasing the velocity by a very, very, very small amount. Isn't that right? I mean, you're already as close, as you know, when you get close to the velocity of light, you know, you're going to put in enormous amounts of energy just to get even a slight increase in velocity. So what's the point? Anyone know? Is it not an awful waste of money then? Exactly, yeah. The velocity may not be increasing much, but the kinetic energy is, because the m there, of course, we slyly just stuck in m without saying what sort of m. But that's a relativistic mass. Once the thing is moving at a fraction of light, that's certainly not its rest mass. And what happens is its mass is starting to increase now. Its mass is starting to increase rather than its velocity. Now, some of you look a little bit puzzled about that, and it reminds me of something I always forget to say. And it's this. This business of relativity is fact. It's not a theory. It's not an idea. We see every single time somebody in the world switches on an accelerator, you see that. The first thing you see is something getting closer. If you look at this figure here, getting closer and closer and closer to the speed of light and never getting there, which in itself is pretty convincing. Second thing you see is the mass of the particles, if you can measure them, is getting heavier and heavier and heavier. The other things you see, by the way, in terms of relativity is where you put the detector is calculated on the basis of special relativity. Because, of course, the particles are moving at the speed of light. Even coming out of the collision, they're moving tremendously fast. So their frame of reference is totally different from ours. And yet we're the ones doing the measuring. So you have to be very, very careful you take that into account. Do you see what I mean? You can't just slap up your detector on a very simple calculation. You have to take the relativistic length into account. The other thing is how long a given particle lives depends on time dilation. Because it's moving incredibly fast relative to you, relative to the chamber or the detector. So the detector has to take into account that its lifetime will be elongated, which is good news, actually. It's the only reason we can measure a lot of them, is that its lifetime is elongated relative to us, time dilation. I'm just mentioning that because, as you know, there was an Irish engineer about 10 years ago. It's when I started getting interested in the public perception of science, who decided, a very good engineer, by the way, but he decided that special relativity was wrong. And he even wrote a book of it. I have the book and everything, and wrote a series of articles, got a tremendous amount of attention in the Irish Times and on the news and all that. And people like me who rang up couldn't get on the show at all because he was, saying Einstein wrong, and everyone in the media thought, great, this is a great story. And no one stopped to ask basic things like, for any physicist, the laboratory of special relativity is, of course, a particle accelerator, because you have something extremely small moving extremely fast. That's where you do the measurements. And I think sadly people like Ronan and other people, they wouldn't even mention this to you because they've lived their whole lives with this. It wouldn't occur to them that anybody questions it. It's just so well established at this stage, and has been since about 1920. Really, it's been there so long that we don't actually no, since the Walton experiment, we don't really question it at all. But we should remind the public from time to time that all of this basically comes down to relativity. If it wasn't for relativity, we wouldn't see the particles at all. They wouldn't live long enough to be seen. It's only because they're moving so fast. Anyway, I digress. Okay, now that's the first part of the talk. In the second part, we're going to do an open bus tour of particle physics, but I promise you it'll be quick. Here it is. The first one is everybody knows about the electron and the proton. The nuclear atom is interesting. We'll come back to it again. It's just the way that was discovered in Rutherford backscattering turns out to be really, really similar to the way that we later discovered the quark. I love the way in science history doesn't repeat itself, but it does rhyme, and you'll see that. The way that they discovered the quark is very similar to Rutherford backscattering. I'm sure you're all familiar with it, so I won't talk about it. What I will say, though, is about 1918, the sort of light bulb dawned, and everybody realized this was the first triumph of particle physics. Everybody realized, well, wait a minute, that's what the periodic table is. Most people don't think of that periodic table in the back of your logbook as particle physics. But of course it is, because the discovery of the proton opened the door to, oh, well, that's the difference between hydrogen and helium. It's just the difference in protons. Lithium has 3. What's number 4? I always forget number 4. Beryllium. Beryllium has 4. See, boring name, that's why I forget it. Beryllium has 4. That's what it is. It's just the number of protons that determine the different atoms. And so once you have that, you have your pattern, and that's the periodic table. As we'll see, that idea then comes back again in a different form later in particle physics. But anyway, I would argue the periodic table depends on particle physics. And then, of course, you had the discovery of neutrons. I just quickly point out where we are in physics, of course, here, in terms of the sort of unification of forces. This is the first hint that, you have the beginning of quantum theory, because it's not clear how on earth the electrons are held in place. Sure, you've got positive nucleus and negative electrons, but why are they sitting there? Why don't they just collapse into the nucleus? Because they're radiating energy. And that was the beginning of quantum theory. But more importantly for us is what on earth is holding the nucleus together? Because if you have 4 protons sitting in a beryllium nucleus, why don't they repulse each other? It doesn't make any sense that they would sit there. And then another question, which they thought at the time was linked to it, is what causes radioactivity? How does that nucleus decay? And we now know, I can't resist pointing out, that actually there are 4 separate forces. There's the familiar force of gravity, which holds things together, particularly in cosmology, because it's a long-range force. There's the electromagnetic force, which normally you don't see because most things are neutral, because it's a very strong force, actually. The electromagnetic force holds atoms together. Now we have to introduce 2 completely separate forces. One is the strong nuclear force, which somehow holds the nucleus together, and one is the weak nuclear force, now known to be different from that, separate from that, which causes the decay of the nucleus by the beta process. Okay, and I just think I've got one quick slide there. Yeah, can I just point out, just to give you an idea of how this sort of works. The theoreticians got to work on that, and they realized, okay, first of all, this strong force is going to have to be a hell of a lot bigger than the electromagnetic force. It's got to be independent of charge because it works with both protons and neutrons. They're both held in the nucleus. And it's got to be extremely short range. Now, if you know your quantum theory, which nobody did at this stage, but as you know, Yukawa was a very, very pioneering quantum physicist, and using Heisenberg uncertainty, he worked out the math and basically worked out that this particle had to be mediating between neutrons and protons and holding together, had to be extremely massive, very, very massive, much, much more massive than the proton. It had to have 3 different charge states, and it was called the Yukawa pion. Okay? I'm just anticipating a little, but I'm just saying that that's how the strong force was discovered. In other words, in theory, they knew this particle had to exist, and then particle physics is all about finding that particle. Now, before we go any further, now we get to mention Walton. At this stage, suddenly particle physics took off because an Irishman, plus Cockcroft, working under Rutherford, discovered how to do these things. Basically, he discovered how to build an accelerator. And what they built was a linear accelerator, which basically functioned as a voltage multiplier, up to about 500,000 volts. Now, of course, in MeV, that corresponds to about 500,000 MeV, which is pretty impressive for the time. But what's even more impressive is that they used it to split the nucleus. They got some, unfortunate lithium atoms sitting on a plate and fired this almighty gun straight at it, actually split the nucleus, and they were able to measure scintillations of helium on a screen, which meant that they had transformed the old dream, one type of atom, into a completely different type of atom. And it's impossible It's nothing to do with Walton, really, to be honest. It's just impossible to underestimate how important that experiment is. It verified so many things at the same time. For a start, it verified mass energy, because the lads not only built this thing, they were also able to measure the energies. The energy of the products afterwards is very important, because if you think about it, when you work out the masses, they don't actually add up. So the big question was, where's the missing mass gone? And it turned out, of course, it's gone as energy. And that was the first really big experimental verification of E is mc squared, because the part of the mass had disintegrated into energy. That's actually what happened. The other thing that a lot of people don't know is that it verified quantum tunneling. Here's your quiz question. Bet you don't know, because nobody ever seems to know, bet you don't know who suggested that experiment in the first place. It was Gamow. Well done. Somebody remembers Gamow. Gamow happened to visit Cambridge that year, and he met Rutherford, and he said, look, I think even though you haven't got enough energy to go into the nucleus, it'll happen anyway if you have enough particles, because of this thing called quantum tunneling I've been working on. It was Gamow. Well done, Dave. It was Gamow who I always think it's such a pity. I mean, that's a third instance where he doesn't get the Nobel Prize for something that he suggested that turned out to be right. It's just incredible. I mean, when Rutherford nominated the lads, he didn't like theoreticians, and he liked Russian emigre theoreticians even less. So he wasn't going to give Gamow any credit. But anyway, let's move on. And the other thing, so that's 2 points about Walton I want to make, is this is the grandfather of all accelerators today. The other point is, I'm going to be a bit controversial and point out, he didn't do this in Trinity, and he didn't do it in Galway, and he didn't do it in WIT. What he did do is he managed, the only reason Walton was involved in this at all was that he was lucky enough to be part of a world-famous group working with the best equipment in the world at the time. That's the reason. Let's be realistic about it. That's the reason he did it. And there's a lesson there which the Irish have never learnt, which is that small countries, we can compete with the best, provided we're at the table. But we need to be part of things like ESO and CERN and things like that to give our students and our young staff a chance. You can't just give a load of money to some bloke in Galway and expect him to do world-class physics. I just don't believe that. I think that's important too. But there's no way that can compete with, say, being a member of CERN, which we're not, by the way, or being a member of the ESO, which we're not. Because you're not mixing with the best people, you're not dealing with the best equipment in the world. For small countries, it's actually particularly important that stuff like this gets done, that we're part of these groups and that we're at the table. Anyway, let's move on. Okay, so that brings us into a whole new area. We're halfway through particle physics now. Now they know how to build accelerators. Two developments then. First, they also began to realize you could also do a lot of nice particle physics with cosmic rays. This was very, very difficult. You had to send up all these balloons into the sky. Of course, no sooner went in the sky and the stupid things froze solid and all the instruments froze. It was terribly frustrating business. But anyway, famously, the first thing they found was the muon. And being scientists, everybody insisted for ages that must be the Ikawa pion. And everybody got tied up in knots. And it was about 10 years before it finally emerged that the muon is a decay product of the pion. The pion is further up again. So that's why it didn't match the properties of the pion, and Yukawa was right all along. It was just took a while to extract that little mystery. Nature loves to play tricks. Anyway, the other thing was, at the same time, particle accelerators began to be built. The clever thing about this is a cyclotron, like you'd see in a hospital. The difference here is, you have a voltage there, but the same particle goes through it thousands and thousands and thousands of times. So you don't need, to build millions and millions of volts. You just need a certain voltage, and then the particle keeps going through it. The disadvantage is, these are two Ds here. They have to switch every time the particle crosses for the whole thing to work. And the problem with that is, again, relativity. What actually happens, cyclotrons are fine in hospitals and stuff like that, but when you get to seriously high energies, there's no way it's going to work, because the particle's perception of time is totally different from the machine's perception of time. And so that led to the idea of the synchrotron. And in a synchrotron, what happens is you have to sync the pulse of the changing voltage with the relativistic time, or the relativistic frequency that the particle sees. And it's all very complicated. There's one other thing I want to mention on that, though. That's why you always see synchrotrons in particle accelerators, not cyclotrons. Then the next step was, somebody finally figured out, of course, the Boy-Racer principle, that you need a collider as well, because if you whack things into each other, you don't lose any energy at all. If you whack something into a wall, a lot of the energy you simply lose. It's actually, in terms of creating particles, far better to collide the particles. Okay, let's quickly move on. I just want you to look at the left-hand side, ignore the rest. Basically, what happened, no sooner had they invented all this, was suddenly you have a huge collection of particles. It's called the particle zoo, or if you like, the periodic table of the particles. Nobody could make any sense of all these particles. And that led to a very famous idea, which is Murray Gell-Mann and Zweig decided that it couldn't be that the proton was fundamental. There had to be something more fundamental again, and this something they were going to call lots of things, partons, quarks, whatever, but quarks stuck. The idea was the quark would be inside, and three quarks up, up, down would make a proton, and up, down, down would make a neutron. That was a completely theoretical idea at first, but it just seemed to make beautiful sense. And then two dramatic things happened. When you do out your special table, you find there's one particle missing, which is the omega minus. And guess what? They went off and they looked for it. And what did they find? But they found the omega minus at exactly the right mass that they were expecting to find it. That was very convincing. But even better, Rutherford came back from the dead. Somebody did an experiment in Stanford where they basically beamed a beam of electrons at a nucleus, exactly the way Rutherford had done all those years ago, but with a much more refined beam. And sure enough, what did they find? They found this thing. Oh, I don't have it there. Blast. Anyway, what they found was it scattered off, suggesting that inside the proton, you had 3 centers of mass. Or inside each proton of each atom, of each nucleus, you would have 3 centers of mass. And that was the first experimental confirmation that quarks weren't just a mathematical idea, that they actually really existed in nature. Now, that said, John Polkinghorne and these kind of philosophy guys love to point out that nobody's ever seen a quark, and that nobody ever will see a quark, and that's actually true. But that's because of their nature. There's this, I love the word infrared slavery, brilliant, isn't it? But what it basically means in English is that as you try and pull them apart, the force between them gets larger. It's the only force in the universe that does that. As you try to pull them apart, the force between them gets larger. So basically, the energy required to produce a separation far exceeds the energy that will create a new quark-antiquark pair. So as soon as you separate them, they basically turn into something else, which is kind of interesting. That's why you can't see one on its own, but it doesn't mean they're not there. Anyway, so we're getting to the end of the standard model. As you all know, eventually, over the next couple of decades, we finally figured out that there are actually 6 of those quarks: up, down, strange, charm, truth, and beauty. 6 of those quarks. Truth, for example, wasn't found until 1996. A lot of people spent their whole careers trying to find that damn thing and never did, because it turned out to be very, very heavy indeed. That's to match 6 leptons. Remember I mentioned the muon. The muon just turns out to be a heavier version of the electron. And there's a third member of that family called the tauon. There's nothing hard or mysterious about these guys. They're just exactly like the electron. They're just a bit heavier. And then they have their associated neutrinos. But what's really interesting about all this stuff is nobody has figured out, see these 2 columns here? Nobody has figured out what they're for. You can make our universe perfectly nicely with these, thank you very much, because the up and down make up the protons and neutrons, the electron goes around the atom, and the neutrino plays a role as well. You don't need any of this stuff at all. So we haven't quite figured out what generation 2 and 3 are for. That's one of the big questions. What are they for? Anyway, moving on. Oh, one last thing, yeah. That's the strong force, and everybody was happy with that. Meanwhile, I skipped a slide. No, I haven't. Meanwhile, something very, very dramatic happened. And I don't want to go too much into the theory, but what happened was, let's just skip down to the third sentence there. A single and it turns out the electromagnetic and the weak forces turned out to be mathematically the same, that you could actually write them down as one type of interaction. And that was a huge step forward. It was the first triumph of a very new type of physics called gauge theory. Nowadays, they say there were 3 revolutions in 20th century physics: relativity, quantum physics, and believe it or not, gauge theory. And unfortunately, none of us, apart from very few theoreticians, none of us understand the word of gauge theory, which is very unfortunate because it's very important, apparently. But anyway, it's mediated, this thing, if it was right, it would be mediated by W and Z bosons. It all sounded like a load of theory, except that it predicted 2 things, something called weak neutral currents, which were measured in 1973, and W and Z gauge bosons, which were measured to tremendous acclaim with a huge amount of applause, blah, 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 in CERN in 1983. And that was the first big, big success of CERN to have done that. Now, so that leads us to this famous standard model, which is where pretty much we are today, is that we now know the strong force is a force between quarks, not between protons. It's the quantum chromodynamics is the fancy word for it. We also know that the weak force and the electromagnetic force are not independent. They're one interaction called the electroweak interaction. Basically, all these forces I'll skip down here are carried by a certain type of boson, if you like, they're kind of messengers. They mediate the force, and they're a type of particle called bosons, which are a completely different type of particle from the particles you and I know. Electrons, for example, and protons and all that. Do you remember all that stuff about Pauli exclusion? That all comes from the fact that the electron has spin 1/2. That doesn't, you've heard of a Bose-Einstein condensate maybe, that doesn't apply to bosons. See, these are obviously very, very different sort of particles. But anyway, that was all the known particles. Here's a nice little picture. Matter, energy, forces. Now the 4 separate look a bit different because these 2 go into one box. The electromagnetic, of course, is mediated by the photon, the weak by the W and the Z, gravity by the graviton, strong by the gluon, and now all of these things have been measured, every single damn one of them. I'll just put that together in a bigger picture till you see it again. The difference now is you can see there's one little snag. There's a snag. I love the little star, isn't it great? Yet to be confirmed. Oh, we are cocky, aren't we? Yet to be confirmed. We don't know yet. We haven't measured it, so we don't know. We've been looking for it for 30 years. So anyway, correct masses, but the Higgs boson outstanding. And not outstanding as in great essay, outstanding and where is your essay? correct masses, but Higgs boson outstanding. Students always misunderstand that word, yeah. The thing is, before I go any further, I just finished the standard model by saying, the thing is, it's not just any old particle. It wouldn't matter if the top hadn't turned up for a while, or the bottom had gone off, or truth and beauty had disappeared or something. We know they're there. But the trouble with the Higgs is it's the one that determines the mass of all the other particles. All of the theory of the standard model, especially the electroweak part, basically it depends on what's known as a Higgs field. It's the interaction of the particles with the Higgs field that give them the masses that they should have. How do we know that? Because when we measure those masses in the lab, they have exactly the masses we expect from the Higgs field. But the embarrassing part is we actually haven't found the particle that pertains to the Higgs field itself. So we haven't found the granddaddy of all the particles, and that's the thing. Is it because it's too heavy? Is it because the debris is just too big? Who knows? Anyway, so we're coming close to it now. This is the very last part of the talk, and it'll be short because there's not much to report. What are the expectations? Well, the number one would be the Higgs boson. It would be nice if that fellow would turn up. It determines the mass of the other particles. We know now it's between 120 and 180 GeV. The latest news, by the way, from Tevatron is it can't. It's got to be below 150. It simply can't be at the upper end of that range. That's been. I'll show you my blog at the end where I report all these things on a daily basis from CERN. But the Americans say there's no way it can be between 150 and 180. So that narrows the window a bit. It's set, of course, because it sets the masses of other particles. Now that we've measured those masses, there is a window that sets the mass of the Higgs boson, if you're wondering, comes from. If you just look at this here, the diagonal line here is the mass of the Higgs. So suppose it was 115. The red is what we used to think was the intersection between the mass of the this is the W boson and the top quark. That now has been improved, you can forget about that red circle, to the little blue circle. So the intersection of the blue circle and the whole green rectangle is the range where we should be looking. So it's getting very, very, in one way it's great, the window's getting very, very small. On the other hand, the chances of it not being there at all are getting very, very large, which is a bit worrying. Now, the reason I say that, and that's where we'll, I'm literally not going to say anything about this. This is just to remind you that this stuff is not easy. I have no idea what half these diagrams are. The basic one, though, is the quark and the quark. See this one here? They're exchanging vector bosons, as in, remember the W and the Z? They exchange vector bosons, and that can create a Higgs particle. But that's only one path. There's dozens of ways you can create a Higgs. There's lots of different ways. Problem with that is you have to work out what would be the decay then. So for example, that's the sort of chart that these guys look at. You know, we don't know, is it going to decay like that or is it going to decay like that? It depends how it's produced in the first place. So basically you're into this sort of thing of there's 100 different ways it might be seen, and that's the most popular one. See that big red one? But sadly, that's the one that's just been ruled out. That lovely peak. Luminosity just means how many particles you see per second per unit volume. It would be great if it had been in that peak, but it's not. Unfortunately, nature has shoved the stupid thing down here somewhere. So it's going to be very, very hard to see if it is down here. And of course, you might say that makes sense. That's why we haven't seen it up to now, is the stupid thing's probably around 125 or something like that, if we ever do find it. Now, one last thing. If you thought that was exciting, you might say, yeah, but it's all about one particle. It's a bit sad. And that's why I want to finish by talking about supersymmetry. Unified field theory was a name given to this idea of unifying the forces. As soon as you might imagine in the 60s and early 70s, as soon as they realized, the electroweak could be unified, everybody started thinking, well, what about the third? Come on, bring in the strong force, and then we'll really have three. Unfortunately, a lot of people, and David Ray asked me to mention my dad, a lot of people, starting with a young Irish physicist called Lachlan O'Rafferty, who were mathematicians, got in the game and were able to show things called no-go theorems. And what the no-go theorems showed was that actually that couldn't be done. Under the reference of under the, let's say, the standard model, it didn't make sense that the strong force would fit with the electroweak interaction. It was simply too different in many ways. Don't forget that thing about as you pulled it apart, it got stronger and stronger. That's very different from the other two. And they were able to show mathematically that it just couldn't work. Unless there was some dramatic new thing, it just couldn't work. The dramatic thing that came along was supersymmetry. What supersymmetry showed was that actually, by the way, GUT, ground unified theory, is the name given to trying to unify the three forces. It showed that in principle it was possible, but only if fermions and bosons are actually not as different as we thought. Or specifically, if every fermion has a supersymmetric cousin called a boson. In other words, if the electron has a cousin which looks just like the electron, but has a spin of 0 rather than a spin of a half, and behaves like a boson. Now, the trouble with that is, as I say down here, nobody's ever seen that, you know. But the bonuses, by the way, is once you accept supersymmetry, number one, all these things at high energy do seem to coincide. But secondly, you get TOE for free, meaning that it also predicts gravitons. It predicts that the theory that would unite the three would also unite all four forces. And that's the famous super force you hear everybody talking about. The reason, by the way, they call it theory of everything, everybody laughs at it, but it's because some idiot called this grand unified theory. So, you know, what's left? What are you going to call the next one? So that's why they call it the theory of everything. Anyway, the phenomenology, as the theoreticians coyly call it, what they mean is nobody's found the damn thing. I mean, nobody's ever seen any one, even one of these. One supersymmetric particle would do. Nobody's ever seen them, and it's never been observed. And then, so that's really what they're looking for. So the last thing, this is the last slide before I sum up. We need then two things. We need, well, first of all, as I say, we would like to finish the standard model by finding the Higgs. On the other hand, we expect to see something beyond the standard model, possibly supersymmetric particles. For example, you might find a supersymmetric Higgs, which would be very nice. The other two questions, of course, like I say, is I just can't resist mentioning that they will also be looking for, number one, why does matter decay in a different way from antimatter? And that's the LHCb experiment. And number two, everybody wants to know just what is dark matter made of? And you'll be pleased to hear the most promising candidate, by the way, is, guess what? Supersymmetric particles, wouldn't that? That would tie very nicely together. If they find a supersymmetric particle, it may even be dark matter, because that would explain why no one has seen it, because it's a boson, not a fermion. Anyway, and this, by the way, is just a picture of, this is how it really happened. We think here's a superforce. Gravity breaks off first. After the next epoch, the strong breaks off. After the next epoch, the weak breaks off, and that's why we see 4 different forces today. And what the accelerators try to do is move back, and the theoreticians are trying to move back even further. Okay, so here's our summary, I think. Oh, yeah, we can forget that. I won't say anything about Rowland's experiment, except to say that they're looking, the particular particles they're looking at is the beauty, the decay of the beauty quark versus the beauty anti-quark. And it's very exciting, actually. Some people say they may even see the Higgs boson in that experiment, in which case they'll see it before anybody else, which would be very nice. OK, so here's our summary. The Higgs boson would close the chapter on the standard model. I don't mean close, because we know it's incomplete anyway, but it would certainly make sense of the, yeah, I'll tell you what, it would make sense of the masses of the particles that we already know. That's the way to put it. It would make sense of everything. On the other hand, we expect to see extensions, hopefully supersymmetric particles. It would open the chapter on unification then, because now we have the third force and possibly even the fourth force in there. Then there's the whole cosmology thing. It would be nice if we knew where the antimatter went. And it would be nice if we had a particle we could say, oh, that's what dark matter is. And then finally, I should mention string theory, because it never seems to get mentioned. The other thing is, we might find completely new things. If we find, for example, new dimensions, higher dimensions than expected, that would be quite a strong indicator that string theory is on the right track. I don't really believe that. I don't see how the hell they're going to see them at that sort of energy. It seems unlikely. But some people say it's quite possible. Lisa Randall seems to think it's quite possible they might actually see evidence of higher dimensions than the 4 dimensions we're used to. And the other thing is they just might find particles that make no sense whatsoever. And that's, as Stephen Hawking says, that's the most exciting thing of all, that they might find something that nobody has predicted. And that often happens in science. Just to say, if anybody you want to look at the slides for this, you'll find the slides on my blog. I won't give you the address. If you just put in the word antimatter and blog, or antimatter and Cormac, it comes up automatically. And finally, maybe I'll finish with that. Look at that funny little picture. It's odd, isn't it? Makes you think. Okay, thanks.